Have you ever heard that reversing a linked list is the fundamental question in any software engineering interview? Reverse linked list is a true pattern mastery 100 staple and frequently shows up at Facebook, Google, and Amazon. Missing this? You're out. Over 40% of candidates get tripped up by edge cases here. Let's guarantee you're not one of them. Let's attack reverse linked list using the basic problem-solving framework, which brings structure and confidence to every interview challenge. Ready? Here we go. Given the head of a singly linked list, our goal is to reverse the list so the nodes point in the opposite direction, and return the new head. Input: head node of a singly linked list, like 1, 2, 3, 4, 5, null. Output: head node of the reverse list, for example, 5, 4, 3, 2, 1. Think about undo operations in text editors. Each action is stored in a list, but when you undo you need to traverse those actions in reverse order. How do you efficiently reverse that structure? Interviewers might even ask, how would you print a linked list in reverse order, or reverse a playlist queue? What makes this tricky? You can't just flip pointers all at once. You need to avoid losing your place in the list. Naive mistake. If you just set node.next equals prev without remembering the next node, you lose the rest of the list. Think step by step. We'll traverse the list with a current pointer. For each node, we'll save the next node, so we don't lose it. Reverse the current node's pointer to point to the previous node. Move the previous and current pointers forward. Let's go even deeper. Imagine you're physically turning each train car around on a track. If you detach a car without remembering where the next is, you'll derail. That's why you always store the next node before changing any links. Edge cases? Empty list, head equals null. Single node, should return the same node. Classic multi-node lists. Here's the plan. Initialize two pointers, prev equals null, cur equals head. Loop while cur is not null. Store next equals cur.next. Reverse, cur.next equals prev. Move forward. Prev equals cur equals next. When done, prev is the new head. Now let's solve solution 1, reversing a linked list using the iterative approach. We'll walk through each line, understand how pointers move, and see how the list gets reversed step by step. Time complexity is O(n), where n is the number of nodes in the linked list. We visit each node exactly once. The idea of iterative reversal: use 3 pointers. Priv tracks the node before current cur. The current node being processed nxt temporarily stores the next node. Walk through the list node by node. Reverse the next pointer of each node so it points to the previous node. Move all pointers forward. At the end, prev will be the new head of the reversed list. Think of it like flipping the arrows of a train track, one car at a time. Line by line explanation of the code. We define a class solution to hold our method. This function takes head, the first node of the linked list, and returns the new head after reversal. Prev will track the previous node. At the start, there's no previous node, so it's set to none. Cur points to the current node we are processing, starting with the head. We loop as long as cur is not none. We stop when we reach the end of the list. We store the next node in nxt temporarily. This is important because we are about to change cur.next. Here we reverse the pointer. The current node now points backward to prev. Think of it as flipping the arrow on this node. We move prev forward. It becomes the current node. This keeps track of the new head as we progress. Move cur to the next node in the original list, stored in nxt. This advances the loop. At the end, prev points to the new head of the reversed linked list. We return it as the result. And that's how this algorithm works. It first initializes pointers, then iteratively flips each node's next pointer while moving forward through the list. Efficient, simple, and elegant. Time complexity is O(n), as we visit each node once. Space complexity is O(1), because we only use a few pointers. The iterative method is easy to visualize and memory efficient. The key is carefully storing the next node before changing pointers. Now that we've implemented our reverse list function, let's see how it works with a sample linked list. This test will show if the function correctly reverses all the nodes, turning the last node into the first, and so on. Let's test it with this input: 1, 2, 3, 4, 5. This represents a singly linked list: 1, 2, 3, 4, 5. Our goal is to reverse the order of the nodes. Here's how it works. We start with prev as none and cur at the head. For each node, we temporarily store the next node, then reverse the pointer so cur.next points to prev. We move prev a and cur forward and repeat until the end. Step by step, the nodes get reversed. 1, 2, 3, 4, 5 becomes 5, 4, 3, 2, 1. The output is 5, 4, 3, 2, 1, exactly what we expect. This confirms our function works correctly. In summary, Our implementation successfully reverses the linked list, handles any list length, and does it efficiently with ON time and O1 extra space. Simple, accurate, and reliable. In this approach, we reverse a linked list using recursion. Each function call processes one node and then lets the rest of the list reverse itself. It's like peeling an onion. We handle the end first, then connect everything back in reverse. Time complexity is ON, where n is the number of nodes in the linked list. Each node is visited exactly once. Recursive calls use ON stack space. Define a class solution in the function reverse list. If the list is empty or has only one node, just return it. This is the stopping point for recursion. Call the function on the next node. This will reverse the rest of the list and return the new head. Take the next node and make it point back to the current node. This is where the reversal happens. Set the current nodes next to none because it will now become the tail of the reversed sublist. Return the new head of the reversed list, which we got from the recursive call. Each recursive call processes one node, and the recursion unwinds from the end of the list back to the start. Space complexity is ON due to the recursion stack. This algorithm first identifies the base case, then recursively reverses the rest, rewiring pointers as it unwinds. Elegant, simple, and very recursive. Let's see how our recursive solution reverses a linked list step by step. We'll test it with a simple input, 1, 2. This represents a linked list, 1, 2. Our goal is to reverse it so that the last node becomes the first. Here's how it works. The algorithm uses recursion to reach the end of the list. When it hits the last node, which is 2, it starts reversing the pointers. Each node points back to the previous one. For example, node 2 points to node 1 instead of none, and the original head becomes the new tail with its next set to none. The recursion returns the new head, which is 2. Step by step for 1, 2. We call reverse list 1, which calls reverse list 2. Node 2 becomes the new head, and node 1's next pointer is set to none. The final list is 2, 1. The output is 2, 1, exactly what we expected. This confirms our function correctly reverses the linked list. In summary, our recursive implementation efficiently reaches the end, reverses the pointers step by step, and updates the head and tail accurately. It works even for small lists, making the solution clear, accurate, and reliable. Breakdown recap. Conceptually, the task is simple. Take a singly linked list and reverse the direction of all its pointers so that the last node becomes the new head. If you think about it, this is like undoing actions in a text editor. You want to traverse everything in reverse order. Assess recap. The tricky part is managing the pointers. You can't just flip links randomly. If you lose track of the next node, the rest of the list is gone. So we compared approaches and chose a safe, iterative method. Traverse the list while keeping track of the previous, current, and next nodes, reversing links step by step. Structure recap. Our plan was straightforward. Initialize 2 pointers, previous and current. For each node, first store the next node. Reverse the current node's pointer to the previous node. Move previous and current forward. Repeat until the end. At the end, previous points to the new head. Implement recap. We implemented this iterative approach, carefully updating pointers at each step. Running it on LeetCode, the code executed cleanly, without errors or lost links. Check recap. We verified the logic with multiple test cases, multi-node lists, single-node lists, and empty lists. Each time, the nodes were correctly reversed, and all edge cases passed. Time complexity is ON, and space is O1, efficient and elegant. Closing insight. The key takeaway? Reversing a linked list is about thinking ahead. Always track your next step before changing links. A small precaution that ensures you never lose the rest of the list. Master this, and you'll handle one of the most classic interview questions with confidence.